Everyone, welcome to this meeting. It's great you are here. And we should continue with probability theory. We should build some mathematical apparatus, continuing what we had the last time. Let me simply share my screen in here. I would like to remind you that we have these materials. So if you follow the sign up link for the quizzes and homework and notes, you will be able to get the materials. If you finish the quizzes and homework, that would be amazing. And for those of you who submitted the answers to the first quiz, thank you, that's great. The quizzes are really designed to find out if you understood the main concepts of the lecture properly. If you did not understand it exactly, maybe if you missed some nuances, these quizzes hopefully will reveal that, and they will also provide you an explanation, maybe further details, and so on. And definitely, I would like the quizzes to clarify all of this. And I see that somebody had a difficulty differentiating sample space and event space. Let me provide a really quick recap in here. And then if people don't have questions, we can proceed. So yeah, we had a big, long introduction. The last time I provided some motivation. I said that in order to avoid paradoxes, we need to actually build a very good mathematical framework, solid mathematical framework. And that framework really builds, well, let me actually make one more distinction here. The framework involves separating the things that are random, so those are described by the probability space, and things that are derived from the random objects. So these will be random variables. So probability space, that's something that we discussed the last time. Today, we should hopefully get to random variables and talk about the things that are derived from the random objects. So what is a probability space? It's a collection of three different objects, specifically the sample space, the event space, and a probability measure. I think I would like to change the color here a bit. So the sample space, that's this omega, that's supposed to capture all of the possible things that can happen, all of the possible outcomes. We had an event space, it's some kind of class of events, and this is going to be subsets of the sample space, and we will assign probability to them. And then we have the probability measure, that's really the probability assigned to these different events in the event space. So let me provide some further reminder here to make sure that things are exactly clear. So we have this sample space or space of outcomes. And I guess it's just a collection of things that can happen. So instead of all possible outcomes, should I remind you of some example? Maybe one roll of a die, right? So this is the set of possibilities. So that's the sample space. Each element of the sample space is one outcome. It's one of the things that can happen. And then if we go to the event space, it's composed of events, and an event is a subset of the sample space. An event is a collection of outcomes. So if you have one roll of a die, you can have an event like this. It would be, say, odd numbers. And you see that an event is actually a set. It's a set of the outcomes. Whereas an outcome was just one value in here, right? So hopefully you see the distinction. This 3 in here, that would be an outcome where you get 3 for the one roll of a die. This event in here, that's a set. It's a set of outcomes. It can have one element, it can have more elements. So that's the distinction. And the sample space is composed of outcomes. The event space is composed of events. So that's the distinction. I hope I explained this well enough, but please tell me if this is still unclear. I can also go here. So sample space, that's the class of events. And yeah, it will satisfy some conditions. We should elaborate on the conditions. We should talk about the sigma field conditions. But after that, hopefully, we can get to random variables. All right, I see that it's clear now. Great. Then we can go ahead and I would like to remind you of the probability measure. So the probability measure is a function. It's going to take as argument or as input events, individual events, and it will output, the functional value of it will be a real number. The real number will be between 0 and 1, so has to be a non-negative number. We have these three requirements for the probability measure. The number has to be non-negative, so the probability cannot be negative. The probability of the whole sample space has to be 100%. And then we have a condition that the probabilities need to add up for disjoint events, pairwise disjoint events. More specifically, if you have a sequence, a finite or infinite sequence of pairwise disjoint events, then the probability of the union of these must be equal to the sum of the probabilities. And this is something we discussed close to the end of the last meeting. So I would like to elaborate on this a little bit more. I would like to provide some further intuition for these requirements. In the end, it's not that complicated, but I think it's just good to present here some explicit intuition. So the intuition for requirement 1 is actually very simple. You cannot have negative probability. Simple as that. For the second requirement, yeah, this is maybe a little bit less trivial. Some people sometimes think that maybe the sample space could have a probability less than 100%. But no, we require that the probability of the whole sample space is equal to 1, meaning that the sample space captures all possibilities that can happen, all possibilities that are meaningful for us for thinking about probability in a particular model. And then we have this third requirement. The probabilities need to add up. And I provided some intuition here. Yeah, let's say you have cards and the probability of randomly drawing a card that is a heart is 30%. Probability of a spade is 35%. Then the probability of a heart or a spade will be 65%. Now, a little bit technical thing in here is that we allow an infinite sequence of these pairwise disjoint events. So it doesn't have to be just a couple of events. It can be infinitely many events, but still like a reasonable infinity. You must be able to create a sequence, ordered sequence of these events if you want to apply this condition. So that's about the probability measure, partially recapitulation, partially further explanation. Is everyone okay with these requirements here? Do we have any questions? Okay, great. Then we can proceed. And one thing that I left out the last time from the discussion, I'm sorry. One thing that I left out was one thing that I left out was the requirements for the classes of events for the event space. And yeah, there's a name for the conditions. the event space needs to form a sigma field. So yeah, sometimes people say sigma field. Sometimes people say sigma algebra. Sometimes you spell it out in English, sigma. Sometimes you use the Greek letter sigma. It doesn't matter. It's all the same concept. And we would like our class of events, our sample space, our event space to form a sigma field. What does it mean? We simply impose a couple of conditions on our event space. It's conditions that are actually very reasonable. Let me talk about them. I think I mentioned it, I'm not sure. But in any case, we may want to spend some time on it today, especially because we will then need it to build a very important concept, the concept of the Borel sigma field. It's something that needs to be defined. It's something that we need to cover. But in the end, when you do some probability calculations, you don't think about it too deeply. So it's something that you see once, and then you just implicitly use it without thinking too much. In any case, so first sigma field. After that, let's talk about the Borel sigma field. We have a couple of requirements. One requirement is that an empty set, an empty event is part of this sigma field. And yeah, we require the event space to form a sigma field. Now let me see, do I have a couple of comments in here? Well, let me provide the intuition immediately. So basically, we want to be able to speak of a probability that nothing at all happens. We want to be able to say, what is the probability of no outcome from the outcome space happening? And of course, we also want to say that that probability is zero. But yeah, we include it explicitly. Then if we have some event A, we also want to allow the complement of that event. So for example, if you have one roll of a die, you can ask, what is the probability of getting number 2? Then the complement of that event would be the event when you are getting some number that is different from 2. And if you assign probability to getting 2, you also should assign probability of getting not 2. And of course, the probability of A and AC, the complement, the probability of these two together must be equal to 100%. Okay, so I'm getting a question. Is the roll of a die can be an example of not having any event? So, well, we always get exactly one outcome, right? And then events can be big, they can be small. Events can include many possible outcomes. They can include very few outcomes. And specifically, this empty set event does not include any outcome at all. So then we simply say the probability of that is 0. It makes our life convenient. So really, there's the distinction between outcomes and events. You exactly get one outcome, but the event may not include any outcome at all. Yeah, question like a roll of 7 with a single die. Yeah, you can formulate it that way. So that would be something outside of the sample space, but yeah, maybe a simpler way of thinking about it is that you have some event that includes some outcomes. If no outcome from the sample space is included in that set, so if the set is empty, then you should have 0 probability. So a little bit of a technicality, but if we didn't make this assumption, then our life would be very challenging when writing theorems and stuff like that. So that's the first and second requirement. And then we have one more requirement. It is that if we have a sequence of events, like A1, A2, A3, can be finite, can be infinite, then we also need to include the union of that. Now that I think about it, maybe I did have some intuition here. Let me open that in a second. But yeah, I'm getting questions. So the complement of the empty set also needs to be in the sigma field. And that's exactly right. So if you just combine requirement 1 and 2, it has the implication that the sample space itself is a valid event. Yeah, I think I had some intuition here. So when I have posted the notes, you can read this, but it's basically what I just said. Maybe to be clearer, what is the complement of a set? It is the set difference. So you take the entire sample space and you remove the elements that belong to A. And that's how you get the complement. And did I have some more intuition in here? Yeah, basically what I said, just to be clear, as for the notation, what does this mean, right? What is this infinite union? It's simply A1 union A2, A3, A4, and stuff like that. So these are the requirements of the sigma field. We would like our event space to have these properties of the sigma field. I will provide some more examples in here to make sure it's 100% clear. Okay, question, what does the A at the end of the third condition mean? Oh, sorry, so this was actually supposed to be F. I previously used the notation A, but this is F. I will fix this in the notes. Just this letter in here was supposed to be the same as this one. That's the F, the event space. Yeah, thanks for the correction. And then, yeah, as for the conditions, let's take a look at an example. It's actually pretty simple. Well, let's think about cards that are faces playing cards. So we will have 12 of them like this. And let's say you have this stack of cards and you can randomly choose a card or randomly draw a card. Then we can talk about different possible events. So one point I want to make here is that the union of events is like the logical operation OR. Let's say we have an event that corresponds to the randomly drawn card to be a spade, and event that a randomly the same randomly drawn card is a queen. And let's think about the union of these two events. So not surprisingly, this is going to include the spade cards, and it's going to include all of the queens. So really union is like an or operation. If you get spades or if you get a queen, then this event did happen, otherwise it did not happen. Similarly, if you have intersections, it's like a logical AND. So if you have the event of getting a spade and the event of getting a queen, you can consider the intersection, and well, it will just have one element. It will be this queen of spades. And finally, you can think about complements. So a complement of an event will be like performing the logical operation not. So you can think about the event of getting a king, and you can think about the complement of that. Well, this will be the set of all the cards that are not kings. All right, maybe I have some further comments, but any question about the meaning of the symbols and stuff like that? Yeah, do you have an example of something that is not a sigma field? It's pretty simple. So the sigma field, again, signifies which sets you include here. And yeah, let's say that we include the set that only contains the King of Hearts and the Queen of Spades. And we have one more set, and we include there the Jack of Spades. So we have really two sets, two possible events. This by itself is definitely not a sigma field. It doesn't satisfy any of these conditions in here. And if you think about it, it would be kind of problematic. So if you had this set, the Jack of Spades, and you assign some probability to it, it would be weird if you were not allowed to talk about the probability of not getting that particular card, right? So that's why we have these requirements. We want to be able to talk about the relationships between the different events and so on. Okay, yeah, so I'm getting a question, is sigma field closed under intersection? And that's very good question. The answer is, it is closed under finite intersections. So not infinite necessarily, but if you just have two events or a finite set of events, if you take the intersection, it will also be included in the sigma field. So that's a good observation. I have it included here as one of the comments. So actually this one. So let's say you have two events, A1 and A2, then you can write the intersection of these as taking the complement of A1, taking the complement of A2, then taking the union of these two, and finally performing a complement operation. Well, then what you get is actually an intersection. So because of this simple relationship, if you have a if you have an intersection of a finite set of sets, then it will also be included in the sigma field. Yeah, so thanks for the comment. And oh yeah, maybe one more comment. The sigma fields, they're not just for probability theory. You will see them in other parts of math as well. Now, I want to kind of aim in the direction of this concept called the Borel sigma field. People often get confused about it. So let me start slow. I would like to talk about the possibility of just taking some set of events that you like and constructing a sigma field from that. Let me jump in. Specifically, let's say that we start with some set of events C. And let's say that this set does not satisfy the sigma field conditions. What we can do is we can just keep adding sets, adding events to our event space until the sigma field conditions are satisfied. So if you start with something that's not a sigma field, you can still fix it. You can still add events to your event space to make it a sigma field. And once you have a sigma field, the probability theory will be much easier to work with. I have some examples in here. Oh yeah, maybe before I go to the examples, let me also talk about this concept of the smallest sigma field. Let's say that you have some events, some collection of events, and let's call it C. And again, it's not a sigma field. You can ask, what is the smallest sigma field in the following sense? You can ask, what is the smallest sigma field such that all of the events that belong to C are in your sigma field? So if the sigma field is capital F, then you would be looking for, we would be looking for a sigma field that contains as few sets as possible, but does contain this C. Now, what I'm talking about here is a little bit abstract. It is to build the concept of the Borel sigma field. If I'm going a little bit too fast, then don't worry, the notes will be posted and I will be happy to answer any questions. And I'm getting a comment here, a question. Using the smallest sigma field, we can express larger sigma fields. Sometimes. So sometimes you would have a big sigma field and it will contain inside of it a smaller sigma field. In fact, probably all of the sigma fields that we typically use will have some smaller sigma field inside. And also if you take this smallest sigma field in here, and if you add a couple more sets to it, and you complete it to make a new sigma field, you will get a larger one. So some examples. Examples of constructing a sigma field from a chosen subset of the sample space. Again, this is not absolutely crucial for the computations that we will end up making in probability theory, but for conceptual understanding, I think it's good to know. So let's say we have one roll of a die. Then we have this sample space, 1, 2, 3, 4, 5, 6. We choose an event, let's say 1, 3, 5, so odd numbers. And we would like to ask, what is the smallest sigma field that contains this event, 1, 3, 5? Well, if we remember the conditions, we can keep adding different sets. So the condition number 1 was that the empty set needs to be included. So that's why we have this one. Then also a complement of any set must be included. So the complement of 1, 3, 5 will be 2, 4, 6. So we definitely need to include this one in the sigma field as well. And we also need the complement of the empty set, which is the whole sample space. It turns out that if you take these 4 sets, they form a sigma field, they satisfy all of the conditions, and you would have some valid probability theory model built on top of that. And the size of the sigma field is simply 4. So what I mean by this F with vertical bars, that's the number of elements. In this case, we have 4 elements in the sigma field. So that would be the smallest sigma field that includes this set. Maybe another example, a little bit more complicated. Let's say that we start with 2 events, 1, 2, and then 1, 2, 3, 4. Then the sigma field, the smallest sigma field, also needs to include an empty set. It needs to include 3, 4, 5, 6, because that's the complement of 1, 2. 5, 6 needs to be included. It's a complement of 1, 2, 3, 4, and so on. So the whole sample space is a complement of the empty set. This set here is a complement. Oh, sorry. We need to have we need to have this set 3, 4. That one is simply an intersection of these two. So we said finite intersections need to be included. And then this one would be a complement of 3, 4. I guess you can provide the argument in different ways, but the conclusion is that these 8 sets together form a sigma field for you, and you will have a valid probability theory model. So the smallest sigma field here has 8 elements. And then do I have one more? I guess it's the same. Yeah, it's kind of similar, but yeah, you can have a smallest sigma field with 4 elements if you start from this 1, 2. A little bit of a technicality, but now let me get to the most difficult mathematical object in here, which will be the Borel sigma field. Before that, do you feel like this is clear? So we simply have some consistency conditions. If we allow ourselves to talk about the probabilities of certain events, then we also require that we should be able to talk about derived events according to these rules. All right, so no questions at this moment. Let me get to this a little bit complicated concept, so something that's actually used to define random variables and things like that. So we need that. But again, if it feels a little bit complicated, don't worry. You will not need to use this Borel sigma field actively when you perform computations. It's just going to be in the background. Okay, question, as I already have a probability model, what is the purpose of building a sigma field? We think about the sigma field simply as a set of consistency conditions. We want to be able to say that, if you have a particular event and you have a probability assigned to it, for example, you should also be allowed to talk about the probability of the complement. You should be allowed to talk about the probability that the event does not happen. And if you did not have these sigma field conditions, then you could start claiming, okay, I assign the probability that the weather will be sunny tomorrow, but I refuse to assign probability to the event that it will not be sunny tomorrow. So that would be a little bit weird. The theorems would become unnecessarily complicated. So we just impose this. We impose this sigma field condition. And if you just have a finite sample space, you can just take the power set. You can take the set of all subsets of it. That by itself is going to be a sigma field, and you're just fine. You don't have to worry at all. So the main reason why we worry is that we also need to be able to deal with real numbers, so continuous objects, and that will be captured by this Borel sigma field. So there it will be a little bit more subtle. So before I jump there, any questions? Everyone okay? All right, so what is this Borel sigma field? Okay, another question. If a sigma field can be defined for an event, then a valid probability model would exist. Well, let me kind of rephrase it. So you can start with an event or a couple of events, and then you can complete the event space by imposing the sigma field conditions. You can ask, so which other events do I need to include? Once you have all of them, once all of this is a sigma field, then yes, you can build your probability model. You can assign the probabilities to the individual sets, and you will build your probability measure that way. All right, thanks for the question. So now to the Borel sigma field. What is it? So intuitively, it is the set of reasonable sets of real numbers. Now here I'm emphasizing just real numbers, so sort of scalar variables. You can do something like that for higher dimensional spaces as well, but let's stick with real numbers for the moment. And then we will talk about the Borel sigma field for the real numbers. And that will be simply a set of reasonable subsets. Now, which exact set is it? So that's explained in here. The Borel sigma field is going to be the smallest sigma field that contains all open subsets of the real line. Again, it's going to get a little bit technical. I may go through it relatively quickly, but if things are unclear, please stop me. I'm happy to explain. So what's a real line? Just the set of real numbers from -infinity to +infinity. What is an open set? An open set is simply a set that does not contain its boundary. So if you have an open subset of the real line and you have some element x in there, then you should be able to create a small interval around that such that the whole interval belongs to your set. So you can have open sets like this, an interval from -4.5 to 4.1, excluding the boundaries in here. You can have a union of sets like this. So these would be open sets. So our requirement in constructing the Borel sigma field is that we simply start with these. We start with all possible open subsets of the real line. And then we simply ask, what is the smallest sigma field containing all of this? And yeah, the answer is that it's something that we will call the Borel sigma field. So maybe a couple more comments. Yeah, sometimes people ask me about a closed set. So a closed set, that would be a set whose complement is an open set. And yeah, the empty set is actually both open and closed. The whole real line is also open and closed. So yeah, what's the point? What's the point? The point is that we will have some big event space. It's going to include events like this. I think I talked about it last time. Maybe a single number, 6.7, or two numbers, set of two numbers, or an open interval from say 301 to 305. We can have some union of open intervals. Also, a closed interval is going to belong there, and a semi-closed interval, like half open, half closed interval, that's going to be included. Yeah, essentially all of the kind of things that you would want to talk about, all of the things that you want to assign probabilities to. That's kind of the main thing that I wanted to say. Really, if we build a probability model, we impose these sigma field conditions. If we talk about real numbers, we start with events that correspond to open subsets. And then we just keep adding additional sets such that in the end, we get a sigma field. If we get the smallest sigma field, that's the Borel sigma field. And yeah, that's kind of the story of the event space for real numbers. In the end, you will be able to do all kinds of computations that you want. So you don't have to actually worry too much about the theory here. Okay, question. If a Borel sigma field must contain all open subsets, does it mean there's only one Borel sigma field? Yeah, it's unique indeed. So it's going to be a unique sigma field. Another question, are there subsets of the real line that are not necessarily in the Borel sigma field? And indeed there are. So you can construct these, you can prove that there exist these paradoxical sets, something that we talked about the last time, not at the technical level, but at the conceptual level. I talked about the fact that there are these paradoxes. Where was this? Okay, oh yeah, I had the links to these paradoxes. So you can have this Hausdorff paradox, and that will include sets like what you're asking about. It's not something that you encounter every day, so you don't have to worry about it for computations, but mathematics need to be rigorous. We should not have any logical contradiction in our framework, and that's why we go through this, through this machinery. We just want to avoid paradoxes. That's why we have it. Once you have it, it's fine. Just like when you drive a car, you don't think every day or every minute when you are driving about the tires of the car. It's the same thing. It allows you to build your mathematical framework in here, but then it's kind of in the background. You don't actively think about it. Another question, does the Borel sigma field satisfy the three condition of sigma field? Exactly, it does. So we start with open subsets of the real line, then we impose the three conditions of the sigma field, and the smallest sigma field that will satisfy them and that contains all of the open subsets of the real line, that's going to be our Borel sigma field. And then we will be allowed to assign probabilities to sets like this. And yeah, obviously it's useful, right? You want to be able to assign probabilities to sets like those listed here. All right. Another question. I think the subset of irrationals might not be in Borel, not 100% sure. Irrational numbers actually do belong to this Borel sigma field. It's because, well, we will have these kind of things in quizzes and stuff like that. So you will have an opportunity to think about what are all of the different objects that belong to the Borel sigma field. But a quick answer is that individual numbers definitely belong to this Borel sigma field. You can ask, what is the probability that your variable is equal to 2 or something like that? Or like that the outcome is equal to 2. And, oh, sorry, I think I misread here. Yeah, the question was about irrationals. Yeah, let me get to irrationals. If you have these individual numbers, if you have events that contain only one number, then necessarily also all rational numbers are going to be there. It's because the set of rational numbers is a so-called countable set. That is, you can write a sequence, an infinite sequence that contains every single rational number exactly once. So necessarily the set of all rational numbers belongs to the Borel sigma field. And then because the complement also needs to be included, also the set of all irrational numbers is going to belong to this Borel sigma field. So if you want to work with it, you can. It will be just fine, and the mathematical framework will hold. The kind of sets that cause these paradoxes or are responsible for the paradoxes, they are even much more complicated than, say, irrationals. And another question, does the fact that the sets are open, does that mean that there are gaps in the Borel sigma field? No. So we will see that in the quizzes. But the open sets, that's just what we start with. We start with the open sets, but then if you just follow the conditions of the sigma field, you will find that, for example, a closed interval also belongs to this Borel sigma field. All right, so this was the main stuff I wanted to discuss today. I was also hoping that I would get to random variables. Maybe I could open the topic here a little bit. I will not be able to explain it in full detail, but yeah, sometimes it's actually better to give people a little bit of time for this material to be digested. So let me open the topic of random variables, talk about it quickly, but since we are close to running out of time, I will leave all the details to the next meeting. Yeah, as I said before, in our probability theory models, we separate the random stuff and the derived stuff. We will have some derived objects, and these are going to be the random variables. So yeah, specifically, a random variable is going to be a function of the elements of the, well, I wrote outcome space, but the proper name is the sample space. So we will have functions that take as argument, that take as input the different outcomes. And then the functional value or the output of this function, that's going to be the realized value of the random variable. That is, you will have a function, it takes as input one particular outcome, and it gives you as output some real number. Specifically, we are talking here about scalar real variables. You can generalize this concept. Now, if you think about it, it may not be kind of the first thing that you would imagine if someone asks you what a random variable is. So with this point of view, there is nothing random about a random variable. A random variable is a deterministic function. It's just that it takes as argument the individual outcomes, that belong to the sample space. Now, yeah, how should I proceed? So maybe a quick example. If I don't have time for the precise definition, we can leave it for the next time. But yeah, well, let's just get familiar with the concept. I keep writing outcome space here, but yeah, the technical term is sample space. Okay, a question. So a random variable maps outcome to a real number. Exactly. So that's what we have here. In the sample space for one roll of a die, we have these outcomes. And let's think about this particular function x. This one will be defined in such a way that if the argument is an odd number, the functional value is 0. If the argument is an even number, the function value is 1. So you can think of it as an indicator variable for getting an outcome that is even. So this is a random variable, one particular case of a random variable. Another, well, I guess for this one, we can say some things about the probabilities. So you can ask, for example, what's the probability of the random variable being greater than 0.3? Well, that's going to happen if x is equal to 1, because the only number that was greater than 0 or greater than 0.3 was 1. So then it's the same as probability of the set 2, 4, 6. And that's just going to be this sum. Probability of getting 2, probability of getting 4, probability of getting 6. And yeah, I think the more complicated example I can mention here, but we will talk about the details of this one the next time. You can have a quadratic function, for example. So that would be a valid random variable. You will have here a sample space that's all real numbers. And once you get an outcome that's one of these real numbers, you can calculate the square, and that's going to be a valid random variable. I guess I have a tiny little bit of time. Let me read here the definition, but the next time we should definitely talk about the intuition related to this, because yeah, sometimes it's a little bit hard to explain. I will have some visualization in here. Yeah, so what is a random variable? A random variable is going to be a function, as we said. It's going to take as argument an outcome, and it will produce a real number. And it will need to satisfy a requirement. We will have that for all elements B of the Borel sigma field, meaning for all reasonable subsets of the real line. If you then go ahead and look up the set of outcomes consistent with the random variable being inside B, then this particular event does belong to the event space. So it's actually a little bit complicated. I will probably need 10 minutes or so the next time to unpack this definition. It may sound a little bit complicated at this moment. In the end, it's relatively simple. You would want to be able to assign probability of your random variable belonging to some reasonable set B. And then the probability of that will be related to the probability of the set of outcomes that are consistent with X being inside B. Yeah, but so an explanation of this is coming the next time. I will have some visualization here and so on. Yeah, so the next time we start with random variables, I will provide an explanation of this definition. And after that, we will be ready to talk about some very useful stuff like cumulative distribution functions, probability density functions, probability mass functions, and so on.